So welcome again in the course module of communication engineering. So far we have discussed about the amplitude modulation in my previous lectures, in which we have already seen conventional AM, DSPSC and SSBSC and vestigial sideband modulation. So now today we are starting one more important modulation scheme whose name is angle modulation. So let's see what is this angle modulation. So you try to see this picture. I have already explained it in my previous lectures. So again, I'm just repeating for your convenience that suppose that if we have a particular carrier and we have a particular massive signal like MT, okay, which is shown in here in this particular picture, okay. So in the case of amplitude modulation, what we are doing is we are changing the amplitude of this carrier in a systematic way with respect to the magnitude of the massive signal. So that was shown in this picture. Okay, here we can see that the carrier's uh, amplitude is actually being varied according to the uh, amplitude of the massive signal that we can see in this particular picture. Okay. Now similarly in the case of angle modulation, okay, right now I am talking about angle modulation. So basically there are two different classes of the angle modulation that we have to study about. So in the angle modulation, we are having two different modulation scheme. One of them is frequency modulation, and another one is as a phase modulation. Okay. So here in this picture, we can see here that in the bottom part, I am showing you an FM modulated signal, which is a frequency modulated signal waveform I have shown. Okay. So here we can see that as we have said in the case of amplitude modulation, that the amplitude of the carrier is going to be varied systematically with respect to the amplitude of the massive signal. Similarly, in case of angle modulation, the instantaneous frequency or phase of the carrier, okay, instantaneous frequency or phase of the carrier is systematically varied with the amplitude of the massive signal. So here we can see that when the massive signal is MT equals to 0, then the carrier will remain unmodulated. And whatever be the carrier frequency, the same frequency that carrier will possess. Now, when this amplitude of the massive signal, if you see, it is changing and it is going high, okay, once it is attaining its maximum value, at this point, you can see that this carrier is having its highest frequency. Okay, its frequency is increasing monotonically. Okay, it is increasing slowly, and whenever this massive signal is achieving its peak value, at that time the frequency of this carrier is also high. Then again, when this is it is going down, when its magnitude is decreasing, then again the frequency of this carrier is slowly decreasing. Once it is becoming 0, again it is becoming the unmodulated carrier frequency FC. Similarly, when it is going down, you can see here when it is becoming negative and it is reaching to its negative peak, at that time the carrier frequency is the minimum. Okay, so here we can see that the carrier frequency is a minimum whenever the massive signal is having its minimum value, and it is having its maximum frequency whenever this particular massive signal is attaining its maximum value. So this is how we perform the frequency modulation. We are just mapping the variation of the magnitude of the massive signal to the variation of the frequency of the carrier. Okay, so this is how we perform. Similarly, we can also show that how the phase modulation is done. Okay, in the phase modulation, obviously the phase will be depending on the massive magnitude. So whenever there is a maximum magnitude, there will be a maximum phase change, and similarly, if there is a minimum magnitude, there will be a negative phase change. Okay, so that we can look at from this corresponding equations. So let us suppose that if we denote a particular carrier, let us say the carrier is generally denoted by this particular equation. Okay, like CT equals to, it is having certain characteristics like AC cos 2 pi FCT plus phi, in which AC is the magnitude of the carrier and FC is the carrier frequency, unmodulated carrier frequency, and phi is the phase of that particular carrier. Okay, whenever t equals to 0, it will be having a phase equals to phi. So now we can see that this particular equation, okay, in which we have three different characteristics of the carrier. One is the magnitude, another one is the frequency, and next one is our phase. So we have already seen that how to vary the magnitude part of this particular carrier, okay. With respect to the magnitude of the massive signal, that was we called as the amplitude modulation. Now we have to look at how this frequency component and the phase part of this particular carrier can be made to vary linearly with respect to the massive signal. And then that time altogether we can call this, it means that if we are calling this entire means angle of this cos as a theta it, which is the instantaneous angle of this particular cosine function or the carrier wave, okay, then this theta it is nothing but 2 pi fct plus phi. So basically, if we are varying this particular angle, okay, either by changing the frequency part or by changing the phase part, okay. So by changing either of them, if we are able to change this angle, instantaneous angle of the carrier, then it is known as the angle modulation, okay. So now specifically, if we are changing the carrier frequency with respect to the magnitude of the massive signal, it is called as Fm. If it is its phase we are changing, then it is called as the phase modulation. Okay, so now just try to understand that what we are saying and what is the mathematical equations, corresponding equations for the case of phase modulation and the frequency modulation. So let us say what is the phase modulated signal. So we are saying that the phase modulation signal, if we are talking about phase modulated signal, then this phase of this particular signal has to be made proportional to varied with respect to the magnitude of the massive signal. Or we can also say that this total angle, okay, this total angle is actually changing linearly with the massive signal, okay. Both are the same thing. So basically the definition of the phase modulated signal you can write in this form, like it is the form of angle modulation in which the angle theta it is varied linearly with the massive signal mt, okay. So either theta it is varied linearly with the massive signal mt, or even you can write that the phase part of this particular carrier signal is varying uh, linearly with the massive signal. So here we can write like phi is equals to kp mt, okay. You can write that phi is directly proportional to mt, and therefore after removing the proportionality constant, we can write the phi equals to kp mt radians, okay. So again, here we can see that what is Kp, as we have defined in the case of amplitude modulation, Ka, that was our amplitude sensitivity of the modulator. It is same as Kp is can also be defined in a similar way, which is nothing but the phase sensitivity of the modulator. Okay. By assuming that the massive signal is a voltage waveform, you remember that I told many of the times that if we are assuming that the mt, which is a massive signal, if it is a voltage waveform, then obviously the phase sensitivity of the modulator will be having its unit equals to radian per volts. If it is an current waveform, then obviously it will be radian per ampere, okay. So that you remember. So now if we take this kp means phi equals to kp mt radians, then I can substitute this phi value into this equation of the instantaneous angle theta it. So that will be equals to 2 pi fct plus kp mt. So basically our angle is nothing but the linearly varying with the massive signal. Okay, its angle is actually, if you substitute phi equals to kpmt, you will find that the angle of this particular carrier is actually being varied linearly with the massive signal. So here we can write this time domain expression for the phase modulated wave SPMT, that will be AC cos 2 pi FCT plus KPMT. Okay, so this is the equation for our phase modulated signal. Similarly, we can again define the frequency modulated signal. Okay, so as we have defined the phase modulated signal, that either its angle, instantaneous angle of the carrier is made linearly proportional to the massive signal, or its phase part is made linearly proportional to the massive signal. Similarly, in the phase modulation, what we need to do is we have to make the instantaneous frequency, okay, instantaneous frequency of the carrier proportional to means massive signal, or you can say we need to make the instantaneous frequency of the carrier linearly varying with the massive signal. Okay, it has to be very linearly with the massive signal. So basically What is frequency modulation? So frequency modulated signal is nothing but it is the form of angle modulation in which the instantaneous frequency FIT is varied linearly with the message signal MT. Okay, it is varied linearly with the message signal. So here you just write FIT. Okay, I have not written here. It is a function of t, so it should be FIT. Okay, you just make it FIT. So basically, what we are trying to say is in the frequency modulation, the instantaneous frequency of this particular carrier is actually proportional to the message signal, and it is linearly varying with the message signal. So it can be defined as FIT equals to FC, which is the carrier frequency, or you can say it is an unmodulated carrier frequency. FC is nothing but our unmodulated carrier frequency plus KF times MT. So again, KF is the frequency sensitivity of the modulator. Okay. So for example, again, its unit will be our hertz per volt. Okay, assuming that this MT is a voltage waveform, right? So this is a frequency sensitivity of the modulator. So obviously, if we make MT equals to 0, it means that the magnitude of the message signal is equals to 0. In that case, this instantaneous frequency will be same as carrier frequency. So this carrier frequency, we can also call it as a unmodulated carrier. Okay, it is an unmodulated carrier. So now just try to assume that, let us suppose that if we have a FM modulator, okay, let us say that we have a FM modulator, and in this FM modulator we are giving a message signal MT. So what is the output of this FM modulator that we are expecting? Okay, that we need to understand. So basically what we try to get is this output of the FM modulator will be a sinusoidal carrier of different frequencies. Okay, of different frequencies. So basically we are interested in the instantaneous frequency of the carrier. Okay, so let us say we are giving message signal MT to a FM modulator, then we are observing what will be the output frequency of this particular FM modulator. So assuming that, let us say that the given quantity for this, okay, KF means frequency sensitivity of the modulator. Let us suppose that I'm just taking for this example like KF equals to 2 kilohertz per volt. It means that it is making a change of 2 kilohertz, okay, per volt. Okay, it will change the frequency of the carrier by 2 kilohertz per volt. Okay, of our message signal. So if we substitute this value Kf equals to 2 kilohertz per volt variation into this equation number 2, you will find that let us suppose that initially we have the carrier frequency equals to Fc. Then if the message signal MT, okay, is taking 2 volts, suppose if it is taking 2 volts, okay, at that time what will be the instantaneous frequency? Here we can substitute it as Fc plus Kf. Kf is nothing but 2 kilohertz. So it is 2 kilohertz multiplied with the 2. Okay, so it will be 4 kilohertz. So our instantaneous frequency will become Fc plus 4 kilohertz. Similarly, if MT is taking 5 volt, we can again substitute 5 volt for MT, and that time our instantaneous carrier frequency will be Fc plus 10 kilohertz. Okay, so you can observe that when our magnitude is increasing, okay, it was 2 volt. So there was a change of the frequency by 4 kilohertz. When it is 5 volt, this change was about 10 kilohertz. Similarly, when our MT is taking a negative value, let us say it is minus 5 volt, then this output instantaneous frequency will be Fc minus 10 kilohertz. So I hope you must be able to follow that. What is this frequency modulation we mean? Okay, so basically the variation in the frequency will depend on the magnitude of the message signal, and it will also depend on the frequency sensitivity of the modulator. Okay, if these two quantities changed accordingly, the instantaneous frequency of this FM modulator can also be controlled. Okay, so now suppose that if we are defining this instantaneous frequency FIT equals to Fc plus KFMT, then in the case of single tone modulation, if we consider the single tone modulation, then MT will be our MT, we can define as AM cos 2 pi FMT. Fine. So now when we define MT equals to AM cos 2 pi FMT, we can substitute into this particular equation number 2. So this expression for FIT, you can write it as FIT equals to Fc plus Kf AM cos 2 pi FMT. Now we know that if this is the equation for the instantaneous frequency FIT for single tone case, then we can observe here that we know that the cos 2 pi fmt will take the maximum value equals to 1 and minimum value equals to -1. So accordingly, we can define what will be the maximum carrier frequency that we can obtain. So this f maximum, you can get it as fc plus kf into am, because cos 2 pi fmt we are taking as +1. So this can be written as fc plus delta f, where we are defining delta f equals to kf am. Fine. So this term delta f, I will tell you later on. This delta f is called as the frequency deviation. You remember that, this terminology. Okay. In the case of frequency modulation, delta f is called as the frequency deviation. Fine. Similarly, what will be the f minimum? So an f minimum will be equals to when cos 2 pi fmt will be taking value equals to -1. Okay. So that time this expression will become fc minus kf am. So that will be again fc minus delta f, because we have defined frequency deviation equals to kf am. So basically this maximum frequency deviation that we are, deviation means it is varying from fc to, there is a change in the frequency from fc to fc plus delta f. Okay, so that deviation we are talking about. So this delta f, we are defining it as kf multiplied with the am. Now you try to understand that exactly what happens when we are doing this modulation. Okay, so first of all, we are having an unmodulated carrier frequency fc. Okay, first we are having an unmodulated carrier fc, and then when we are having a positive message signal, okay, mt, then at the maximum value of the mt, the carrier frequency is going to change by plus delta f. Okay, as we can see in this particular equation, that we are going to get the maximum frequency equals to f maximum. So this is, we are going to get this plus delta f. So we are getting a maximum frequency value will be equals to fc plus delta f. Similarly, if we are getting a negative value of mt, then for the minimum value of the mt, this fc is going to be reduced. Okay, here it is increasing by delta f and it is becoming fc plus delta f. Here it is reducing by minus delta f, and then the minimum frequency will become fc minus delta f. This is how our frequency is actually made to vary with respect to the magnitude of the message signal. Okay, in a similar fashion, you can again observe in the case of phase modulation. Let us suppose that if the initial phase is phi equals to 0, if there is no phase, okay, phi equals to 0, when message signal is absent, okay, if mt equals to 0, then if there is a there is a positive value of mt, then there will be a net change in the phase that will be denoted by delta phi. As we have already defined that phi will be equals to kp am. So that maximum value that will be we will be getting it as phase deviation will be equals to kp am. Again here it is, if it is mt is minus, then there will be a phase deviation negative phase deviation will be occur, and that will be equals to minus kp into am. Okay, so again we can see that initially we do not have any phase, but here it is, phase is changing by changing the magnitude of the message signal, and it is ranging in between minus kp am to plus kp am. Similarly, here you can observe that the phase, the frequency of this carrier in the case of FM modulation is actually varying from fc minus delta f to fc plus delta f. So what is the total change, total swing in the frequency? Here we can see that, so that total swing is of 2 delta f. Okay, you can directly calculate this fc plus delta f minus fc in bracket. So what, how to calculate the swing? Fc plus delta f minus in bracket fc minus delta f. So we are going to get 2 delta f is the frequency swing. It means that it is the total frequency variation from minimum to maximum. Okay, from minimum to maximum. What is the total change in the, or total swing of the frequency? Okay, so that is defined as the swing. You remember that many of the times in the competitive examination, it has been asked what is the swing. Okay, if the delta f is given, then what is the swing? So swing should be defined as 2 delta f. Okay, sometimes it is also defined as plus minus delta f. Okay, so you remember that if we want to calculate the swing in magnitude form, it should be 2 delta f. Fine. So this will be the swing. Now you just try to make a comparison with respect to the AM modulation. In the case of conventional AM, we have seen that our unmodulated amplitude of the carrier was AC. Okay, whenever we are giving a plus empty signal, okay, means whenever we are giving a positive message signal, amplitude of the message signal is positive, then this net change in this particular amplitude that was observed is plus mu AC. Okay, and therefore its amplitude, if you remember, we got the maximum amplitude of the AM signal was AC1 plus mu, and similarly we got the minimum amplitude of the of the carrier signal was AC1 minus mu, if you remember. Okay, we have already seen this one. Okay, we have already seen this one. So whenever we have the minimum magnitude of the massive signal, the modulated wave, AM modulated wave was attaining this particular magnitude AC1 minus mu. Okay, and the maximum was AC1 plus mu. So similarly, we can also understand the variation of this frequency in the phase when we are changing the magnitude of the massive signal. So now try to look at the time domain expression for the FM signal, frequency modulated signal. So once we understood that one, okay, how we are defining the angle modulated wave. So basically we are defining the angle modulated wave as ST equals to AC cos theta IT, okay, where theta IT is nothing but the instantaneous angle of the this particular carrier, okay. So based on how this theta IT has been changed, whether the phase is changing or we have made the frequency of the this particular carrier proportional to the massive signal, it can be either defined as the phase modulated signal or the FM modulated signal. So right now we are talking about the FM modulated signal. Now you try to understand how to look at this particular signal. So this signal can be considered as a phasor of magnitude AC. Okay, so you can see that this is a cos theta IT. So basically, if you try to draw this particular waveform, we know that there will be a cosine variations. Okay, or we can also say that there is a phasor of a magnitude of A. Okay, whose magnitude of A is actually rotating with a constant speed. Okay, or that speed may be depending on the instantaneous angle of this particular cosine wave. Okay, so basically you remember that if we are talking about the oscillation, okay, or the frequency, how we talk about the oscillation, what will be the oscillation? So oscillation means that whenever this angle is making a rotation of 2 pi radians or 360-degree angle. Okay, so once it is making a 2 pi radian rotation or 360-degree rotation, okay, that time we are calling that one cycle has been done, or it is completed, or it has completed one particular oscillation. Okay, so let us suppose that if we are talking about the instantaneous angle of this particular carrier, then if we talk about the average frequency, okay, average frequency in hertz over an interval from t to t plus delta t, because we know that this instantaneous angle of this cosine wave is changing monotonically with respect to time. As the time progresses, this is also making an angle. Okay, it is also making an angle. Some rotation is taking place, and suppose that at this point t equals to 0, or you can say the time is t, and in between t and t plus t delta t, it has been rotated up to this point. Okay, let us say from here to here, it has been rotated. Okay, so now we want to calculate what is the average frequency. Okay, what is the average frequency in hertz when this phasor has been rotated in the interval of t to t plus delta t. Okay, so I'm saying that let us say at this moment it is t, and in between t to t plus delta t, it has been rotated by this much amount. Okay, so up to this point it has been rotated. So if it is rotated this much, then we have to calculate what will be the average frequency of this particular phasor. So how to calculate the average frequency? We need to calculate what is the angle rotated. What is the final angle? Means theta I t plus delta t minus initial angle theta I t. Okay, then divided by 2 pi delta t. It is the interval in which it has been rotated. Okay, so this way we can calculate the average frequency of this particular phasor which has been rotated over a time interval of delta t. So after calculating this, we will be able to calculate the average frequency. Now, if we wish to calculate what is the instantaneous frequency of this particular phasor, okay, then how it can be calculated? We can calculate the instantaneous frequency FIT by just substituting this limit. Okay, limit means when the time interval is very small. Okay, so when delta t tends to 0, then this will be if we substitute this limit to this particular equation, average frequency f delta t t, then this will be giving us the instantaneous frequency of this particular phasor quantity. Now If you substitute this limit delta t tends to 0, theta it plus delta t minus theta it divided by 2 by delta t, we'll find that this is the definition of our derivative. Okay, time derivative of the theta it. So differentiation, fine. So this is the basic expression for the differentiation. So what we can write is the instantaneous frequency fit of this particular equation, okay, that can be written as 1 upon 2 pi is the constant term, so it will be written as 1 upon 2 pi, and now the rest of the quantity will become the differentiation. Okay, so it will be a time derivative of the instantaneous angle theta it. So it is d theta it upon dt. So that will be our instantaneous frequency. So now we can have the definition of the theta it, another definition, how this theta it can be calculated from this equation. So theta it can be calculated by calculating the integration over the time interval of 0 to 2, 0 to t, okay. 2 pi will be multiplied over here, and this is our instantaneous frequency fi tau d tau. So why we are tau? Because it is a dummy variable. Just for the integration purpose, we have taken it to be a dummy variable. So this is another definition of the theta it that we can write instantaneous frequency, which is 2 pi 0 to t integration over 0 to t fi tau d tau. Now we have our first definition of the theta it as we have defined it as fit equals to fc plus kf mt. Now what we can do is we can substitute it for this into this particular equation. Okay, so we can substitute of the definition of the fit that we have chosen in the last definition. So if we substitute this, what will be the equation? Theta it will be becoming 2 pi 0 to t fc plus kf m tau d tau. Okay, so now after doing this integration, we will be able to get this theta it will be equals to 2 pi f ct. Okay, you just try to do this integration, we will be getting 2 pi f ct, then we will be getting 2 pi kf, and then 0 to t and m tau d tau. So basically this is our basic definition of the theta it for the fm case. So if you substitute this theta it into this expression, okay, this expression will be becoming for the time domain expression for the fm modulated wave. So what we can write, sfmt will be equals to ac cos, and then we have to substitute this instantaneous angle, that will be 2 pi fct plus 2 pi kf and integration over 0 to t m tau d tau. So this is the basic definition, time domain expression of our frequency modulated wave. Okay, this is the basic definition. Okay, this is the standard expression for our fm modulated wave. Now if we take the case of single tone modulation, okay, so what we do is we can substitute here massive signal mt will be equals to cos am cos 2 pi fmt. Okay, so that we can substitute over here. Okay, so you just substitute, and just to change the dummy variable, okay, t should be replaced by the tau. So here you will be getting am cos 2 pi fm tau d tau. Okay, and then if you do this integration, we will be getting AC cos 2 pi fct plus 2 pi kf. This is the factor 2 pi kf. And then it is AM 2 pi fm, and this will become sine 2 pi fmt. Okay. So here we are getting this particular equation in which this 2 pi will be cancelled out. And then we will be getting an equation like SFMT equals to AC cos 2 pi fct plus kf multiplied with the am divided by fm sine 2 pi fmt. So you remember that in the final equation, I have replaced kf am divided by fm equals to beta. Okay, I have replaced this quantity kf am divided by fm equals to beta. So I have defined this beta equals to kf am divided by fm. Okay, where kf am we have already defined, and this quantity is defined as the frequency deviation delta f. Okay, so it is delta f divided by fm, and this is called as the modulation index for frequency modulated wave. Okay, you remember that this is our modulation index. This is the definition of the modulation index in the case of fm wave. So I hope this discussion must be clear how to get this particular equations. Okay, so this is the standard equation, okay, for single tone modulation. Okay, this is the definition of the modulation index. Here one observation that we have to make is we have also defined the modulation index for the conventional AM. If you remember, we defined it as mu equals to KAAM. Okay, it was KA multiplied with AM. But here if you see, this modulation index is being defined as KF AM divided by FM. So basically, if you see the difference, the modulation index in the case of FM, it does depend on the message frequency. It just does depend on the message frequency. Okay. But in the case of conventional AM, it was independent of the message frequency FM. Okay, so I hope this discussion must be clear. If you having any query, any doubt, you can please drop me message into the comment box. Okay, so we will be discussing this topic further based on this value of the beta. Okay, at present I have just defined the expression of the beta, which is nothing but the frequency deviation divided by the message frequency FM. Okay, so based on the values of the beta, if beta is less than 1 or greater than 1, we can define the two different type of frequency modulated scheme. One of them is called as the narrow band FM and another one is called as the wide band FM. So that we will be will look at in the next coming lectures. So please stay connected with this channel. If you have any query, please drop me a message in the comment box. So thank you for watching. Stay connected with the channel for more updates. Thank you.